Hi everyone and welcome to this video. Today we're going to be speaking about Newton's law of universal gravitation. Um, I know quite a lot of people struggle with this section, but it's actually quite a simple section in physical science. So let's try to clarify some of the misconceptions and things you don't understand. So the first thing to know, what is Newton's law of universal gravitation? Well, the law basically describes the gravitational force experienced between two objects of mass. So if I have a mass m1 and another mass m2, in the universe, these will attract each other. That's the reason why the Earth rotates around the Sun, the Moon rotates around the Earth. It's because of a gravitational force. That's the same reason why we stay on the Earth. What's important to know is the main formula for calculating this force is any gravitational force is equal to constant g times the mass of object 1, mass of object 2, and divided by the square of the distance between them. Now, lots of people get hung up on this guy over here, the square of the distance between them. That is the distance between the center of mass. So if we're looking at this object here on the left, the center of mass is right here, just underneath that M. And the center of mass of this guy, of M2, is about here. So the distance between the two objects is actually that distance there, and not this distance here, not from surface to surface, it's from center to center. And that's a really important thing to understand. Very often you'll have a question where you have something like the Earth and you have a satellite. Actually, we're going to do an example like that soon. So you have a satellite. Let's see if we can draw a satellite. Yes, it's really small compared to the Earth. And then they ask you something to the effect of calculate the weight of the satellite or the force of gravity by the Earth on the satellite, and then lots of people would take that distance when in fact the force of gravity between two objects of mass is the center to center distance. So the center of the Earth is way down here. You can see that just on the bottom of the video. So you'd actually have to take that distance there. Okay, important thing is force of gravity, right? It's otherwise known as weight, right? We call it weight when we're on Earth. And the force of gravity, obviously a force is a vector, so it has magnitude and direction. And according to Newton's third law, if object A exerts a force on object B exerts an equal but opposite force on object A. And that force is attraction. So you can see here with these forces over here between M1 and M2, they're equal but opposite, and gravity is always an attractive force. So that's all there is to it, really. Just another thing about force of gravity, we have kind of a shortcut on Earth for calculating the force of gravity. We call it our weight. Now, it's important to distinguish between weight and mass. Remember that weight is a force. Weight is also equal to G, whatever you want to call it. There's a force and is measured in newtons. And our mass, well, mass is mass, I guess, and it's a scalar quantity and it's measured in kilograms. So that's really important to understand the difference between the two. Now, you've seen the equation W equals mg, where this is mass and this is gravitational acceleration, usually 9.8, and it's meters per second squared or meters per second squared. Okay, so that's how we can work out our weight on Earth. But what is weight? Weight is basically another word for the force of gravity, because That's measured in newtons, and that's how much the Earth pulls us down when we're on the surface of the Earth. Now notice that 9.8 over there, that we can only use that when we are on the surface of the Earth. That's really, really important. Okay, so we use this little shortcut to work out our weight. We just go our weight, which is a force in newtons, is equal to our mass times gravitational acceleration, which is 9.8. And that only applies for the surface of the Earth. If we go any higher, like a satellite, we can't use that 9.8 because the further and further and further we get away from Earth, the smaller and smaller that g becomes until we in space and effect that g effectively becomes zero. We become weightless, so we don't feel that force of the Earth, force of gravity. Okay. Yeah. So let's go on to an example. Scroll down here, and we are going to be talking about an example. Oops. With a satellite, and it was one of the examples people struggled with in one of the past exams. Let's have a look at it here. This was a question in Fairmont High School's June 2014 physics paper, and it said the SunSat 1 is South Africa's first satellite that was built at Stellenbosch University by electrical engineering students. The mass of the satellite is 64 kilograms and orbits the Earth between 620 and 850 kilometers. I forgot to put that in kilometers. Oh no, there you go. Kilometers above the surface of the Earth. Okay, so I've told you got the satellite, 64 kilograms. That's its mass, right? It's mass, not its weight. It's mass. That's really important to understand the difference. Mass is 64 kilos. So even do this in the exam. Take a highlighter, take a colored pen. Right, colors stand out nicely, and just underline all the important facts. So the mass of the satellite is 64 kilos and orbits the Earth between 620 and 850 kilometers above the surface of the Earth. That's super important. Not above the center of the Earth, above the surface of the Earth, and you'll see why that's important now. Okay, so the first question is state Newton's law of universal gravitation. This is a really easy law to state because you can basically just write down the formula and then read off the formula. So we just get a different color here. See if this one stands out. We know the formula is force of gravity is equal to constant m1 m2 over r squared. Okay, you don't need to write this down. It says state, so you're going to be writing words. So I'll show you how to interpret the formula and then basically just read off the law using the formula that you have in your formula sheet. So what are we speaking about? We're talking about the force, the gravitational force, And what is this force between? It's between two objects of mass. That's really important. So between two objects of mass. Now, when we're saying laws, we never say things like equal to or not equal to. We say things like proportional or inversely proportional to. So the gravitational force between two objects of mass, which is this guy here, is directly proportional to the product of the masses, right? Because they're on the top of the fraction, and inversely proportional to the square of the distance between them. And that's as easy as that. You just read it off the formula. So the gravitational force between two objects of mass is directly proportional to the product of their masses and inversely proportional inversely proportional to the square of the distance between them. And the handwriting is just getting worse. Between them. And whenever you write a law, you just want to read through it one more time, just to make sure you've written everything in proper English. So the gravitational force between two objects of mass is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. 100%, you'll get your 2 marks for that. Super easy. All you have to do is go to your formula sheet, Newton's universal law of gravitation. What formula do we use for that? Fg equals g m1 m2 over r squared. And you basically just read the formula. Remember, directly proportional to the variables on the top, inversely proportional to the variables on the bottom. We don't include this g because this g is what transforms proportional to equals. So that g is just a constant, so it's not a variable, so we don't include it in the law. And the next question is, let's just get a different color. Next question is, what is the weight of Sunsat 1 on Earth? Okay, by that they mean on the surface of the Earth. So remember we said we had that nice little shortcut that we could use. Let's see if this works. There we go. What is the weight of Sunsat 1 on Earth? Well, we know the mass of the Sunsat, we'll just say m of s, is equal to 64 kilograms. All right, we're given that. And that's all we really need to know because we want to find the weight of Sunsat on Earth. And we have a nice easy formula that goes W equals mg. Okay, so that's the weight on the surface of the Earth, is, or the force of gravity, the same thing, is equal to mass times gravitational acceleration. And that mass is, always substitute in brackets, 64 kilograms, g is 9.8 on Earth. And that's equal to, I had to grab my calculator there, that is equal to 627.2 units. It's weight, so it's a force. So it is newtons. Usually we have to give a direction because force is a vector, but it's implied that the weight is going straight towards the center of the Earth. Okay, nice and easy. You got your 2, maybe even 3 marks if you're lucky. You got your 2 marks there. Nice. You got one more question to do, and then you got Newton's universal law of gravitation, or Newton's law of universal gravitation, waxed. So let's try this last question. Let's just scroll up a bit. There you go. Prove that the weight of the Sunsat 1 is approximately 23% less when it is orbiting the Earth at a distance of 850 kilometers above the Earth than when it is on the Earth. Take the mass of the Earth to be 6 times 10 to the power 24. That's what that little copy means. Kilograms. So that's really heavy. And the radius of the Earth to be 6.4 times 10 to the 6 meters, right? 6.4 million meters. Okay. And they say, what are you trying to do? Let's look at this question and actually try and understand what they want us to do. They want to basically compare the weight of Sunsat when it is at a distance of 850 kilometers above the Earth and when it is on Earth. Okay, and what are we comparing? The weight. And they say, prove that the weight of the Sunsat 1 is approximately 23% less. So that's the answer we're looking for. We need to do some kind of calculation that verifies that the weight of the Sunsat 1, remember weight, force of gravity, due to the Earth, of Sunsat 1 is approximately 23% less when it's higher up, right? You expect it to get less when it's high up until it's super high and it's in space and it's basically weightless. There's 23% less at a distance of 850 kilometers above the Earth, which is above the surface, than when it is on the Earth. Okay, so let's first draw a sketch, and I'm going to write everything down, we have it all nicely here. So we know our weight on Earth is 627.2 newtons. That's what we know. That's what worked out in the previous question, right? Over here. Okay. We know the radius of the Earth, which is what they give us, is 6.4 times 10 to the 6. Was that meters? The mass of the Earth was that 6 times 10 to the 24. Kilograms. Yeah, masses in kilograms. And the answer we're looking for is 23% less when the Sunsat is orbiting the Earth at 850 kilometers. Okay, so height, we just call that maybe h is equal to 850 kilometers. And weight nu is equal to 23% less than weight, right? Which is the weight on the surface of the Earth. Let's quantify that mathematically. If it's 23% less, that means for every 100, 23 less. That means that it is equal to 100 minus 23, which is 77% multiplied by the old weight, which is equal to 0.77 times W. Now that's a really important thing to understand, because if you don't understand that, you can't answer the question properly. You will get method marks, but you won't be able to answer the question. So be sure that you know how I got 23% less than W is 77% of W. Okay. Right, it's the same concept as if something at the shops is 60% off, that means you're only paying 40% of what it was. Okay, so just check your maths on that one. But let's try answer the question. So let's draw a picture first. So here's the Earth, right? Super big. And here is the satellite. And we know the weight of the satellite on the surface of the Earth is 627.2 newtons. Great. Now what we want to know is the weight of the satellite 850 kilometers above the surface of the Earth. Okay. And what is the formula for that weight? Well, Fg, the same as weight, is equal to G m1 m2 over r squared, straight out of your formula sheet. Okay. Great. Okay, so let's fill in everything on our picture over here. So we know this height h is 850 kilometers. We also know that the distance to the center of the Earth, in other words, the Earth's radius, about their center, it's not maybe to scale, is 6.4 times 10 to the 6 meters. You can fill in symbols like RE for our Earth and H, or you can fill in the numbers, whatever you feel more comfortable with. Now the mass of the Earth. Okay, I'll just fill in the symbol. I don't feel like writing it. And what else do we know? We also know the mass of the satellite here, ms. Okay, so do we have everything we need to calculate the weight of the satellite here due to Earth, right? By the satellite having mass and being here, it's experiencing a force. Let's change color to show force. So it's experiencing a force down towards the Earth, and believe it or not, the Earth from the center is experiencing a force upwards towards the satellite. Okay, Newton 3. So how do we calculate that force? We substitute into this formula here. So do we have everything? Let's check that first. M1, okay, let's take M1 to be the mass of the satellite. We know we're given that. Mass of the Earth, yep, got that. Constant always. Distance between them, right? That's the distance between the center of them, right? So we know that distance, that's the radius of the Earth. Okay, it's see this distance. Yeah. Okay. And we know the distance from the surface of the Earth to the height of the satellite, 850 kilometers. So we can add them and get the total distance from the center of the Earth to the center of the satellite. So we have the distance and we can square that. So we have everything to work out the force of gravity or the weight of the satellite at 850 kilometers above the surface of the Earth. So let's substitute in. So G is 6,67 times 10 to the minus 11. M1, which is mass of satellite, 64. Mass of the Earth is, where's it gone? There, 6 times 10 to the 24, significantly larger than the satellite's mass, divided by the distance between them squared. Okay, so what is the distance between them? Let's fill it, remember, fill it in brackets, and then we'll square it. So the distance is that radius of the Earth, 6.4 times 10 to the 6. We're working in meters, remember, SI units, meters, kilograms. So it's that distance there, plus that distance there, and that distance is 850 kilometers. So how many meters is that? 850 kilometers is 850,000 meters. And then we square it. That's really crucial, to square it, the total distance. Okay, you can't square individual ones. You have to get the total distance, square that, and work that on your calculator. And you should get 487, you can round up 3 newtons. Okay, and what did we have to prove? Well, we knew that on the surface of the Earth, the weight was 627.2. Now we've worked out the weight, right, force of gravity, at 850 kilometers above the surface of the Earth, and that's 487.3. And let's just go back to the question. Question said, prove the weight of the Sunsat is approximately 23% less when it's that high up, when it's 850 k's up above the surface of the Earth. Okay. So we use this expression here, that the new weight must be 23% less than the old weight of W. So what did we actually need to get? Let's just take this down here. What we actually wanted to get was 77%, or 77 over 100. That's what 77% means. Multiplied by, I'm looking over here, multiplied by that old weight, which is the weight on Earth, which is 627.2 newtons. And let's just put that into our calculator. 627.2 times 0.77, 482. You can round it up to 483 newtons. Okay, now that is really, really close to 487. It's pretty much 23%, 23, right? So you have therefore proved that the weight of the satellite at 850 kilometers is 23% less than the weight on the surface of the Earth. So when you're approaching these questions, just think logically. Remember, distance is the distance from the center of one object of mass to the center of the object of the other object of mass. Remember to use meters and meters, right? Always convert to meters. Always use kilograms and kilograms. That's really important. And then just have a clear idea of what you're actually calculating, and you shouldn't have any trouble. Good luck with the exams coming up, and I'll see you in the next video.